Dear students, I welcome you for the today's lecture related to the vessel supports, where we are going to discuss the designing of the skirt support. In general case, the vessels they are supported with the either of type of the support, that is the skirt support, bracket or lug support, saddle support, and the leg support. Out of this, the leg support, which is considered to be the basic and primary, and it can be used as the simple welding of the legs or simple welding of the pipes, or the angles to the basic vessel. However, the use of this leg support is limited to the small dimensions of the vessel, that is of a small vessel capacity of 1 to 2 meter cube, that is used by the leg supports. Now, when the skirt support is there, it is used for high vessels, means the tall vessels. The bracket supports or lug support, that is L by D ratio is 2 to 3. That means your diameters are from 2 meters to 5 meter, and heights are not more than 10 meters or 15 meters or so. And generally these bracket supports or lug supports, they are used in the location inside the buildings. If the vessel is inside the building, then this bracket support or lug support, they are more preferred. And the fourth one is your saddle support, which is used for your horizontal vessels. That is, for horizontal vessels, we are using the saddle support. The pipelines which you can see on the road side or besides the road, there are certain saddles, concrete saddles, which are provided, and on those concrete saddles, your pipes, they are getting supported. So this saddle support is for your horizontal pipes. Now coming to the design of the skirt support, that is the generally the distillation columns, absorption columns, and extraction columns. These are your tall vessels where the diameter of the vessel is say 1 to 2 meters, and the height can go up to the 20 meters, 30 meters, or 50 meters. Sometimes can go to the 100 meters also. That depends on diameter and the product requirement. So generally you can say the 20 meters to 50-meter height, which is a very tall height. And there you are going to use the skirt support. It is similar to the skirt. That is where the outer diameter of the outer diameter of the vessel, that will be equivalent to the inner diameter of the skirt. That is, the outer diameter of the vessel will be same as that of the inner diameter of the skirt. However, the bottom diameter of the skirt, that may vary. That can be the parallel, or that can be the more than the vessel diameter. So depending on the expanding or parallel type of the skirts, these are the dimensions that will be generally used. Then basically the skirts are welded at the bottom of the vessel and rest over the bearing plate. So the bottom, it is welded. Now these are your welded joints or attachment of the skirt and the vessel, and at the bottom this certain bearing plate that will be provided, and this bearing plate which is resting on the concrete foundation. That means below this plate there is a concrete foundation that will exist, and on this concrete foundation this bearing plates that will be there, means all these are your bearing plates. So this bearing plate, that is forming a complete periphery, and this bearing plate that rests on the concrete foundation, and where the skirt that is welded here. Now in this case, the inside welding that is also there, as well as the outside welding that is also there. That depends on the process requirement. Now what are the different loads that will be acting on this bearing plate? So while designing, I am going to be interested in calculating the thickness of the skirt. That is one thing. And second, that is related to the thickness of this bearing plate. So the two things that is to be calculated. One is the thickness of the skirt and the second thickness of the bearing plate. So while designing this, we are going to calculate the skirt thickness and the bearing plate thickness. So what are the different loads that will be acting on these bearing plate? They are to be first calculated, and then we are going to calculate the stresses. So one thing you have to remember, that the first thing is that you are going to calculate the load. What is the load acting on that part? The load, the different types of the loads that will be acting. Then we are going to calculate the bending moment, and then we are going to calculate the stresses. So this is a three-step process. Even in case of your shaft designing, we have calculated the load, the bending moment or the torque, and then finally the resultant stresses we have calculated. Similarly here also, we are going to calculate first the load, then the bending moment, and then the stresses because of that particular aspect. So what are the different aspects that will be acting on this? One is its own weight, weight of the vessel, that is going to be acted, plus the weight of the contents. So that has to be balanced. That is first initial thing. The stresses due to the dead weight, and the dead weight of the vessel plus the operating weight of the vessel, that we will account. So the total weight summation W, this will incorporate the dead weight of the vessel plus the operating weight of the vessel. That means the vessel contents, weight of the vessel contents, that is to be considered, plus the dead weight of the vessel. Dead weight of the vessel means the metal weight, weight of the metal. So total weight of the vessel plus the liquid content or the solid contents. Now this will be acting on this skirt. So the total weight that is to be transferred to the skirt. So this the stresses, which is nothing but the weight per unit area. So this is the area on which the total weight that is going to act. It is the total weight which is getting acted on this particular area. So कौन सा एरिया है कि जिसमें डेड वेट एक्ट हो रहा है, किसको बियर करना पड़ रहा है, कौन से एरिया को बियर करना पड़ रहा है. So that is the, its pi d is nothing but your circumference, that is the pi d. Now if I am going to put a support here, so what is the weight of the vessel that will be acting on this area? So this area, यहाँ पे weight act हो रहा है, तो कौन सा area है ये? That is the thickness or circumference, that is nothing but your pi into d. That this area you can see, the pi d is this area into the thickness which is going to act. So this is the supported or balancing weight, total weight of the vessel and its content which is acting on this support. It has to be balanced by the thickness and the circumference of the vessel. So that is why it is considered to be as the pi dsk into the tsk, because the stresses which is equal to the weight per unit area, weight upon area, and weight is nothing but your total summation of the weight. summation of the W that incorporates the dead weight of the vessel plus the operating weight of the vessel upon the area on which this total weight that is acted. So that is the pi dsk into the tsk. Then the next is your the lateral load by retaining the thermal growth of the interconnecting pipes. Then the wind load which is acting on the vessel, and the next is your seismic load. Seismic load, that is nothing but your earthquake. And calculate the skirt thickness, that is most important. Skirt thickness and the thickness of the bearing plate, that can also be calculated. Now the next is stresses due to the wind load. Now on which surface area this wind load that will be acting first. Now let us consider this again as a column. On this column, the wind that is getting exerted, this is the wind force that will be exerted. So the surface area, outer surface area which is exposed to the wind. Now if this vessel that is getting insulated, तो इंसुलेशन का भी फेसल थिक डायमीटर कैलकुलेशन में अकाउंटिंग होगा. So that is why you have to take the diameter of the vessel plus the thickness of the insulation, so that the total weight of the total diameter of the vessel that is to be taken into account. If I am going to say put this insulation, so I have to consider the diameter of the vessel as the diameter with the insulation. So my total diameter that is going to increase when I am going to put the insulation over that. So the wind forces acting over the lower region and upper region of the column. Now there are two sections which is taken into account for this column. If the column height is more than 20 meters, assuming that this column it is having the height more than 20 meters. Below 20 meters, it is one load that is acting, wind load that is acting over the lower region, and the wind load that is acting over the upper region. So the wind load that is acting over the upper region, that means height above 20 meters, that is to be taken into account. If this is the column having the height more than 20 meters, then the wind force which will be acting on the column, that is, say this height up to this height, it is the 20 meters. So height up to the 20 meters is this part, and the height above 20 meters, that is the upper section, you will be considering this. So this is the height above 20 meters and the height below 20 meters. Why this has been taken into account? Because as we go up and up, your wind load that is going to increase. So up to 20 meters height, the wind load that is taken as the lower values, and which is taken as 100 kgs per meter square. So P1, that is the wind pressure acting over the lower region of the vessel, that is height up to 20 meters. So its value is taken as 100 kgs per meter square. And above 20 meters, that means in the upper section of the vessel, the wind load is taken with a more value, that is 200 kgs per centimeter per meter square. It is, the units are kgs per meter square. You have to remember the units also. That is 200 kgs per meter square. That is, the P2 is nothing but the wind pressure acting over the upper region of the vessel above a height of 20 meters. So this is above the height of 20 meters, it is 200 kgs per meter square. And below this, it is the 100 kgs per meter square. Now, instead of defining these two different, I can make a combined also. If say my height of the column is say 35 meters total, that means 20 is in the lower region and 15 meters is in the upper region. So average of this I can also take into account. In some numericals, I can be given a single value. Even the height is more than 20 meters, then I'm going to take the average value, that means more than 100 kgs per meter square. Say 140 kgs per meter square. This value I have assumed for my calculation, 140 kgs per meter square. So this is the load which is acting on the vessel. Now looking at this, say up to this point, its the height is 20 meters. Above it, it's a 15 meters height. That means lower section, the load acting is only 100 kgs per meter square. And above this 20 meters height, the load acting is 200 kgs per meter square. But some numericals, they for simplicity of calculation, they can assume the height, a total height of say 35 meters or 45 meters or 50 meters, and can take a certain average value of 140 meter per kgs per meter square, or 160 kgs per meter square, or 170 kgs per meter square. Again, that depends on the location and the wind load. If the winds they are more frequent and with a high velocity, they around your seashore, then this becomes more critical. Now the from the wind load, one has to calculate the wind force. So what will be the total force that is acting over the lower region of the column, and the wind force acting over the upper region of the column. So I have to calculate the wind force based on this wind load. P1 is the wind pressure. It is nothing but the wind pressure that is acting. So P1 is the wind pressure and PLW, that is the wind force. So P1 is the wind load, a wind pressure. Then this wind pressure is having the value of 100 or 200 or say 140 or 150, that depends on the area and that depends on the height of the column. So PLW, that is for the lower region, that is K1, K2, P1, H1 and D0. DE0 is nothing but DO, outer diameter of the vessel. Now if the vessel diameter is with the insulation, then I have to take into account the outer diameter plus the thickness of the vessel, so that I will make a total vessel diameter. जो कुछ सरफेस एरिया एक्सपोज होगा विंड को, that vessel diameter has to be accounted. So this is the wind force acting over the lower region of the column, that is PLW, which is K1, K2, P1, H1 into the DO. And similarly PUW, that is the wind force acting over the upper region of the column, that is the PUW, which is nothing but K1, K2, P2, H2 into the DO, where this H2 is above 20 meters. That difference has to be remembered. So P1 is nothing but the wind pressure. H1 and H2, these are the heights. H1 is up to 20 meters, H2 is about 20 meters. DO is the outer diameter of the vessel, or the outer diameter of the vessel plus the thickness, 2 times the thickness, that will make the total diameter. Then the K1 and K2, these are the constants depending on the shape factor and depending on the period of vibration of the vessel. K1, that is a shape factor of the column. Now shape factor of the column, that can be either cylindrical surface or a flat plate. Generally for our columns, we consider it as a cylindrical surface. But however, there are the walls, uh, building walls are there, or some restrictions are there, the flat plates are used. In that case, this K1 factor will have the value of 1.4, and in case of a cylindrical surfaces, this K1 will have the value of 0.7. And K2, which is the another constant. This is the coefficient depending upon the period of one cycle of vibration of the vessel. That means the period of one cycle of the vibration of the vessel. This is what the vibration that will be exerted because of the wind. So as I am going to apply the force, wind load, wind force that will be exerted. So whatever these, that is going to give a tilting motion, and your vessel that may get the vibrations even at a height. You can feel these vibrations when you go to a certain height. There one can feel these vibrations. That is what the period of one cycle of the vibration, that is taken as K2, which is equal to the 1 if the period of vibration is less than 0.5 seconds, and K2, that is equals to the 2 if the period of vibration is more than 0.5 seconds. So that depends on K1 and K2. K1 is depending on the shape factor, and K2, that depends on the period of vibration of the vessel. So we can calculate the PLW, that is the wind force, because of the wind pressure. Then we have to calculate the bending moment. So bending moment, that is nothing but the overturning moment in this case. For overturning, as I am applying the force, it will get overturn. यहाँ से overturn हो रहा है, so that it is getting overturned. So the bending moment, that is the overturning moment at the junction of the column and the skirt. At the junction of the column and the skirt, यहाँ पे वो overturning होगा. Then for the vessel having the height less than or equals to the 20 meters, my bending moment formula is nothing but the wind force multiplied by half the distance, h by 2, that is the wind force PLW into the h by 2, that is generally your bending moment that is taken at a half a distance. So wind force which is acting on this vessel, we are going to average in this case, that is related to half the distance has to be taken into account. So whatever the h that will be there divided by the 2. So total height h by 2. So रिजल्टेंट जो फोर्स रहेगा वो h by 2 पे एक्ट होगा. So this is the resultant force, and that is why the bending moment, which is equal to PUW, wind force, into the h by 2. This is for the height less than 20 meters. Now if the height is more than 20 meters, what will happen? That is PLW into h1 by 2, where h1 is the 20 meters and h2, that is about 20 meters. Say for example in a height of a column height of a 35 meters. So this H2 will be 15 meters in that case. So this is PUW, which is H1 plus H2 by 2, where H1 is 20 meters and H2 is total height minus H1. Now, this bending moment that is calculated. After the calculation of the bending moment, the stresses exerted because of the wind load that is to be calculated. So the stresses, which is nothing but the bending moment upon the Z, that is your sectional modulus. So this the sectional modulus of the skirt cross section. So sectional modulus, which is nothing but the I upon Y. I is the moment of inertia about the neutral axis upon the distance from the neutral axis. So this is Z, the section modulus, which is nothing but I upon Y. I is moment of inertia about the neutral axis upon the distance from the neutral axis. So this is the Z, which is nothing but pi by 4 dO square into the TSK. dO square into the TSK. Then this is for the stresses because of the wind load acting at the bottom section. Now next is the stresses because of the seismic load that is to be calculated. Here in the above cases, we have first calculated the wind force, then the bending moment because of the wind, and then the stresses because of the wind. Now, similarly for seismic load also, we are going to calculate the first load we are going to calculate, then we are going to calculate the bending moment, and then finally we are going to calculate the stresses. So again the three steps. So coming to this seismic load that is nothing but your the because of the earthquake, vibrations because of the earthquake. So vibrations because of the earthquake, when we are taking into account, it is the lowest at the bottom and the maximum at the uppermost section. So it induces the vibrations in the column, and the stresses induced can be the tensile or compressive in nature. नो दी वाइब्रेशंस हो रही है इसमें, तो यहां से एक साइड से वो कॉम्प्रेसिव है और दूसरे साइड से वो टेंसाइल है. So on one side the vibrations are compressive and another side that is it's a tensile in nature. So that depends again on the which side I am going to take the stresses. So load force that will be is equal to F, which is equal to CS into W. CS is nothing but your seismic coefficient. CS is nothing but your seismic coefficient. Now where this load will be acting, that is 2/3 from the base of the column. The height 2/3 from the base of the column. So this will be taken as your resultant stress. In the previous, it is the half the total distance, but in this case where the seismic load, the vibrations are maximum at the top, and that is why we are considering this acting at a height of 2/3 from the base of the column. So these are the resultant force that is to be taken into account from the 2/3 height from the bottom, or you can say from the surface of the earth. So it depends on the period of vibration, and the minimum value of this coefficient CS, that is nothing but 0.05, and the maximum value is 0.08. So this CS is nothing but your seismic coefficient and having the value of 0.05 and maximum value of 0.08. In general case, the maximum value should be considered for the estimation of stresses induced. The next is your the bending moment induced up to the height h, height x, measured from the top of the column. So bending moment because of the seismic load, that is what ms, the bending moment because of the seismic load, that is nothing but the ms, and at a distance x, which is equal to cs into w, that is nothing but cs into w is the total weight, and that becomes your f. This is your f into the distance upon the x upon the 3 into bracket 3h minus x upon h square. Now this bending moment at the base of the column, which is taken as the two-third the height. Now in this case it is at a distance x measured from the top of the column. So this is x square into 3h minus x upon s square. That factor has to be added. So this is the bending moment at the base of the column. This is nothing but two-third into the cs into w into the h. So once the load and the bending moment that is calculated, then the stresses that will be calculated. The stresses because of the bending moment, that is FSB, which is equal to MSB, that is bending moment because of the seismic load at the bottom, upon the Z, the sectional modulus. Z, which is nothing but I upon Y. I is the moment of inertia, and upon the y is the distance from the neutral axis. So that makes your pi by 4 into do square into the tsk. So this is the stresses induced due to the seismic load, seismic bending moment at the junction of the column and the skirt. Now, the possibility of wind load acting the seismic load and the wind load simultaneously is very rare. So, out of this, which is more, that is to be taken for your calculation. So, that is FWB or FSB, that is stresses because of the wind load at the bottom or stresses because of the seismic load at the bottom. So out of these two, which is the maximum that is to be taken into account for your calculation purpose. Now, so what is the wind load? That is, this is the application of the wind load. So as a result, on this side, it's a compressive in nature, and on the another side, it is the tensile in nature. So compressive हो रहा है, तो it becomes the addition. Now what is the weight of the vessel and the weight of the contents that is acting in a downward direction, and this wind load which is acting is going to try to uplift, overturn it. So this is, they are in the opposite direction when you are taking into the tensile in nature. So this stresses because of the tensile, maximum tensile stresses, which is nothing but the either of the higher values of the wind load or seismic load minus the stresses because of the dead weight, that is FDB. The stresses because of the dead weight acting at the bottom, and the maximum compressive stresses in the skirt wall, that is the compressive. So it becomes the summation of either of the higher values of the wind load or the seismic load plus the stresses because of the dead weight. So this stresses should be less than the permissible stress value of the material. So whatever the stresses, the compressive and the tensile stresses will be calculated, that should be less than the permissible stress value of the material. Since this skirt is cylindrical, it is welded joint efficiency has also to be considered. Then if the skirt is conical, half the top angle is say maximum 10 degrees. be considered while deciding the permissible stresses. So at that the J cos alpha has to be taken into the account. So F tensile is less than or equal to F into J cos alpha, and F compressive, that is less than or equal to 0.125 E into the cos alpha into the T upon D SK. So to simplify the procedure for estimation of the skirt thickness, the skirt thickness TSK is assumed. Now everywhere you are taking into account the TSK thickness. So then and only then, if you know the thickness value, then and only then you will be able to calculate the stresses value. So the stresses value, and finally the compressive stresses, and finally the tensile stresses, that is to be calculated, and it has to be compared with the permissible values of the material that is to be taken into account or can be compared it. The next is the bearing plate. So this is how the thickness is assumed, and can be verified whether the assumed thickness is suitable or not. So T thickness, skirt thickness is assumed, and calculate the various stresses mentioned earlier, that is the tensile stresses and the compressive stresses. If the maximum stresses induced is less than the permissible stresses, then the final thickness can be selected. So the selection of the skirt thickness is easy in these processes. Now the next is the selection of the thickness of the skirt. That is what we have first calculated. So this is the skirt thickness that is to be calculated. Now the thickness of this bearing plate, that is also to be calculated. So for that purpose, the skirt bearing plate, that is to be taken into account. So whatever the total weight that will be acting, the maximum of that will be the for compressive stresses. So the maximum compressive stresses between the bearing plate and the concrete foundation, compressive stresses ऐसे ओवरटर्न हो रहा है वो, तो इस साइड में compressive stresses act होगी because of the dead weight. यहाँ पे dead weight हो रहा है plus the इधर से wind force का भी weight act हो रहा है. So it's the compressive stresses that is maximum and has to be taken into account. So summation of W upon the area, that is nothing but pi into the dsk upon tsk, plus the bending moment because of the wind or bending moment because of the seismic load upon the Z sectional modulus. So the thickness of the bearing plate that can be estimated by considering the uniform cantilever beam with the FC as the minimum load. So maximum bearing plate thickness, that is to be calculated by using this formula, M maximum, which is equal to FC into B into L square upon 2, where L is the outer radius of the bearing plate minus outer radius of the skirt, and B is your circumferential width of the bearing plate. B is the circumferential width of this bearing plate. Then the maximum stresses induced in the bearing plate. So this bottom plate is the maximum stresses. So it is the 6 times the maximum bending moment. So 6 times the maximum bending moment upon the Z, that is the B into TB square. That is where TB is the thickness of the bearing plate. So the stresses induced in the bearing plate should be less than the permissible stresses of the bearing material. Then this has to be opposed by the anchor bolts. Now whatever the bearing plate that is there, and if I am going to anchor the bolts here so that the overturning will be avoided, इधर में मैं bolting कर दूंगा तो it will not get overturned, ऐसे tilt नहीं होगा. यहाँ पे जब मैंने anchoring कर दिया है, so that the anchor bolts, they are embedded in the concrete foundation and are required to prevent the overturning of the vessel. So that is what the basic purpose of the anchor bolt, to avoid the overturning of the vessel due to the bending moment induced by the wind load or the seismic load. जो कुछ application of force हो रहा है उस vessel पे, उसको oppose कर रहे हैं ये anchor bolts. Now these anchor bolts are provided by deciding the stability of the column. Now what is the stability of the column? The vessel itself is a stable, right? I have not provided any support for this. Vessel is just simply on this earth surface. So the vessel without support also is a stable. Why? Because of its own weight. जो कुछ वेसल का वेट प्लस कंटेंट्स है उसके कारण वो वेसल स्टेबल है अभी. But as I am going to apply the force, the vessel will face the vibrations and it should not get overturned. So that I am going to prevent this overturning by applying the anchor bolts. So this is the minimum stresses induced in the bearing plate which we have taken into minimum stresses. Minimum stresses is the total weight of the vessel upon the area, that is the because of the dead weight. Stresses because of the dead weight minus stresses because of the either the wind load or the seismic load, whichever is the higher one. So this wind because of the dead weight minus Mw or Ms upon the Z sectional modulus. Now if Fc is positive or 0, Fc is nothing but this is what the Fc minimum stress is. So Fc is 0 or positive, then the estimate the stability coefficient of the column. If Fc is positive or 0, then we will estimate the stability of coefficient for the column. So stability coefficient, that is nothing but the bending moment because of the weight upon the bending moment because of the wind or seismic load. So bending moment W minimum into the R upon Mw or Ms. So M weight, that is the bending moment due to the minimum weight of the column, due to the minimum weight of the column. So empty condition में भी वो stable रहने चाहिए. Vessel without contents, if it is exposed to the air, that is the bending moment due to the minimum weight of the column that is to be taken into account. So R is the bend moment arm for minimum weight of the vessel. Then the R, which is equal to 0.42 into the DO. DO is the outer diameter of the bearing plate. If Y is greater than the 1.5, that is the Y is nothing but your stability coefficient. If it is greater than 1.5, it means the vertical column is sufficiently stable. If Y values, that is stability coefficient values, are sufficiently are more than 1.5, then the column is said to be the stable. There is no need to prove. There is no need to provide the anchor bolts. So the vertical column, if the stability coefficient is greater than 1.5, then there is no need of providing the anchor bolts because the weight of the vessel itself is sufficient to prevent the overturning. Overturning because of the wind load or seismic load. इतना स्टेबल है, इतना मोटा आदमी है, तो उसको धक्का मारने के बाद में कुछ फर्क पड़ने वाला है क्या? नहीं. So it is the weight of the vessel itself is very stable.